All right, our last speaker in this morning's session is Aarna Garg, who's joined us from UC Santa Cruz. Aarna's been working this summer with Allison and Peter, and today she'll tell us about their project together, Understanding the Star Formation Rate Discrepancy, a study of hidden active galactic nuclei.
Thank you, Gwen, and thank you all for being here. So, star formation rates. These are a measurement of how many solar masses are turning into stars per year in a galaxy. And usually in these star-forming galaxies, we see massive stars on the orders of 10 to 100 times the mass of our sun, and they emit in the UV. So what they do is they ionize the gas around them into what we call H2 regions, and these dusty H2 regions will take the UV light, reprocess, and re-emit it into the optical and near infrared wavelengths, which is what we detect. And the key thing about these massive stars is that they have really short lifespans of about a few million years. So they're excellent probes for star formation rates because we know that if we see massive stars in these galaxies, then star formation must have happened recently. So what you're seeing here are the pillars of creation, and not pictured are massive stars to the right of it, illuminating the environment in the ultraviolet. And each of the colors that you see represent the different common star-forming elements. So the dark blue is oxygen, the green is hydrogen, this dark red is sulfur, and the orangish red is nitrogen. And these large dusty pillars is where the star formation is happening. And what's really cool about star formation rates is we can map them into star formation rate densities. So these are good probes of the activity level of the universe. It's basically the star formation rate per unit volume, usually megaparsecs cubed. And what you see here is a famous Maddow and Dickinson plot of star formation rates against time. So we have redshift and we have look back time. And so you want to look at time from going to right to left. So this is closest to the age of the universe, and this is present day. And this can tell us a lot about the metallicities of the early universe, how many stars are forming. We see this peak in star formation rate from the start of the universe until a redshift of 2, and then a decrease until today. So this can also tell us about how much cool gas there was early in the universe and how much fragmentation was happening. But as we remember from the pillars of creation, there's all this dust that's surrounding these massive stars. And it can often block the light that's getting to us, and we can underestimate the star formation rates. So an alternative is radio, because that's dust unbiased. So we focus on synchrotron emission in this project, and what happens is that around these H2 regions, electrons are excited by supernovae and other high energy events. And what they do is they bend around the magnetic field lines in these H2 regions, and they emit radio waves about 1 to 10 gigahertz, which is what we detect. And synchrotron is a really sensitive star formation rate tracer. It can probe up to a redshift of 5, which is really important and really cool. But there is, of course, a problem that we must solve. So we have this UV-IR spectra and we have the radio emission data. But the issue is that they're not giving us the same results for our star formation rates. So recently, Allison confirmed a 50% increase in the star formation rate densities in the radio regime compared to the UV-IR spectra. So she took about 3,800 galaxies in the Deep 2 sample using Meerkat, so using synchrotron emission, and compared it to the Maddow and Dickinson line that we saw earlier, which is just looking at ultraviolet and infrared data. And the main takeaway is that this solid line, which is the radio emission star formation rate line of best fit, is not matching up with the Maddow and Dickinson curve. So there's at least a 50% discrepancy, sometimes even 100%. So what we're seeing is that we're just either overestimating the star formation rates in the radio regime, or there's something else we're missing and not understanding. So one of the solutions I was looking at this summer was whether active galactic nuclei, or AGN, could be the source of our star formation rate discrepancy in the radio regime. So AGN are these supermassive black holes that are feeding on gas and dust, and the ejected material from the black hole gets bent around the magnetic field and has these giant jets, and these electrons are really, really accelerated, making them super luminous in the radio. So what could be happening is that we're mistaking AGN-dominated galaxies as star-forming galaxies and just overestimating the star formation rate in the radio regime. So what's really cool about our project is we can do a direct apples-to-apples comparison. So we took 150 radio-selected star-forming galaxies from the same Meerkat Deep 2 sample, This is the Meerkat telescope. And then we took spectra, UV, IR spectra from the Magellan telescope. And then we can compare directly the UV optical IR star formation rate measurements versus the radio data star formation rate measurements for the same exact galaxies. So before I start talking about our methods and our results, I just wanted to walk through once what an optical spectrum of a star-forming galaxy looks like. So there's a lot of emission lines, and the ones that we care about are H alpha and H beta, O3, N2, and S2. So hydrogen, oxygen, nitrogen, and sulfur. And what you can do with these lines is you can calculate nebular line ratios. So how much light is coming to us from these specific lines? And you can take certain ratios that can be metallicity and ionizing diagnostics. So one really important one is O3 over H beta. And we can do the same with N2 over H alpha and S2 over H alpha. And then we can create this visual diagnostic map to characterize our galaxies called the BPT diagrams. So you can see the nebular ratios on the axes. They're both against O3 over H beta. But on the left, we have nitrogen over H alpha, and on the right, we have sulfur over H alpha. They both look at, okay, what regions are star-forming galaxies? How many of our galaxy samples are actually forming stars? The nitrogen BPT looks at this composite region, which is a mix of star-forming and AGN. And then both plots look at where AGN lies in the sample. But the sulfur plot goes a step further and characterizes the AGN into high ionizing and low ionizing galaxies. So this can further test, okay, if we do see AGN, what types of AGN are we looking at? What would their spectra look like? So then we start with our sample. The first step was to calculate how far in the universe are we looking at? How far are we probing? And in order to do that, we needed to cross-correlate our observed spectra with template spectra from the Sloan Digital Sky Survey data release 7. And the highest correlation point is where these spectra line up the best, the highest match. And then you plug the lag into the Doppler shift equation and it spits out a redshift. So most of our sample lies between 0.3 and 0.4. And now that we have the redshift, we can shift back our observed spectra into the rest frame spectra. So what does the light look like in these galaxies before it reaches us? And from there, we can pick out emission lines. So you see N2, H alpha, sulfur. And remember, these are the 5 important lines from these star-forming regions. And then we can finally figure out how much light is coming to us from these lines. So we needed to fit a Gaussian into the emission line and calculate how much light is coming from underneath these curves. So some priors I fed the code was the amplitude and the mean. So if we take this H alpha line, the amplitude is about 1. And then we know that we expect H alpha to sit at 6,563 angstroms. So that's another prior we can feed the code. And then it just calculates the area under the curve. So we get all these line fluxes for each line. And then we can calculate specific line ratios, which allows us to plot it on the BPT diagram. So what you're seeing in gray is the Sloan Digital Sky Survey data release 18 as just a comparative measurement to see how our points trend. And in the black is our sample. So we do see a few AGN candidates and some composite, but most of them are lying in the star-forming regions. But we can't directly say whether or not AGN are a source of the discrepancy without looking at the radio. So this is the same exact plot, the same exact points, but now with the radioluminosity color map. So here is a direct apples to apples comparison. We expect AGN to be more luminous because of those giant jets. They're super bright in the radio. So we would expect them to have more of a yellowish color on this color map. But as you can see, they're very green, so they're not that luminous. And in fact, some of our star-forming galaxies are a lot more luminous than the AGN. So the mystery remains. We don't know what's really going on. We have to do some further classification. So the main point of this project is, okay, there's this difference between star formation rates in radio and UV optical IR, where the radio, we're just getting higher star formation rate measurements. And our BPT diagram suggests that AGN may not be the case for this discrepancy. We have to do further classifications. So I'm currently looking at broadline analysis to see whether there are other sources for this discrepancy, like maybe supernova winds that could be mimicking the spectra of AGN and falsely classifying our galaxies. And then once we get our flux calibrated, we can actually calculate the star formation rates and see how well our points lie up. Thank you.
Great, thank you, Aarna. Do we have questions? Anna?
Because it turns out there's multiple reasons something is happening. So it looks like you at least have some AGN in your sample. So how, what fraction of that star formation rate that's being tested can be attributed to AGN, even if it's not like the full amount that.
Right. So that's a really good question. And Gwen brought this up in the practice presentations, like how much of your data are overlapping. And so I wanted to see, let's see, where is it? Yeah, okay. So what you're seeing here is the overlap between our data. So these are the only two that overlap, and these are the only two that overlap. So I think we're only seeing like 2 AGN out of the whole sample. So I don't know how much of that we can contribute to the discrepancy, because we might be misclassifying these if there are other sources that are accelerating the electrons to that speed. So yeah, until we actually start calculating the star formation rates, I would be surprised to see whether these AGN are actually contributing to a lot of the star formation.
Other questions for Aarna?
Comparison between the two different estimates for self-measurement, right? That's what you can do on a galaxy by galaxy basis as well as like average.
I do think so. I don't know the exact like statistics behind that because we haven't really calculated our specific sample, but I think you can do a galaxy to galaxy comparison, which is what we're trying to do with our sample. We have both diagnostics. So yeah, that would be interesting to see rather than an average, whether each galaxy spits out like the same star formation. Yeah.
Other questions for Aarna? Great, let's thank her again.